Okay, see you. All right. Um, let's start. Sorry to be about 5 minutes late. Let's do it this way. All right. So last week, I think we ended at MPEG 1. So just to say about the rest of the course, we have this week and next week, and then we're completely done. At the beginning of next week, we're going to have a lab tour. So we're going to meet here in this room, but then try to be on time, because immediately afterwards we're going to go just around, just down the hall to our lab. And then you can see some of kind of the 3D display and acquisition and printing things that we have in our lab. So hopefully that will be fun. And then we'll come back and finish up with any material that we haven't finished. Then we can have an open question session. So be sure that'll be kind of your last chance to be in a room all together, able to ask questions. So be prepared for that. Yeah, and then it will be just the end of the course. You have your deadline for your projects that you have to submit, and then there will be the final exam, an oral exam. So are there any questions on that, or are we ready to go into MPEG standards, last bit of MPEG standards? All right. So we talked about the overall layout of MPEG. It's quite simple. This diagram is quite simple. But the idea is that you have a medium. So it could be a disk. It could be transferred from a file over the network, however it happens. And then you have a medium-specific decoder that decodes to a standard stream, right? So there's an ISO standard for that stream. And then that gets split into three components. There's the audio, video, and clock, so that you have an alignment between audio and video. And then you'll have an individual audio decoder, depending on how the audio is encoded, right? So you can have a lot of different standards for that here. And you have a video decoder as well. And then that both of those are going to be communicating with the clock control to make sure that you have alignment between the different channels. And then the audio gets piped out to the speakers, for example, and the video gets piped out to the display. And we talked about how the video is encoded. And remember, we're using predictive coding for this, right? And so the more information you have, the better predictive coding you can do, right? So the better prediction you have, the less residual information you have to encode, and the lower the rate of information transfer you have to make, right? The higher rate of compression you'll have. And so you have this sequence of pictures. The pictures are blocked into groups of pictures, right? And then what we're going to have are different types of images in the sequence. You're going to have an I image, which is where you transfer the entire image with no prediction whatsoever. You just transfer all of the information, right? So there's no dependency on previous or subsequent frames, which means that if you've had some sort of glitch in your transmission and your picture is looking bad, this is your chance to recover from that error and start sending the signal. Then you have the P frame, and the P frame is predicted from the I frame or another P frame. Okay? And so these are going to be spaced regularly between the I frames. And then in between those, you're going to have, for this shorter type of motion, you're going to have the B frames. And the B frames are actually going to have both a forward and backward prediction. So you've sent the P frame. If there's been all of the rate of the, if all of your encoded data has been transmitted correctly, then you have 100% of the information for I and P at the point of trying to predict the B frames. Okay, so you have both a forward and backward prediction from I and B. so that you can try to get a very good estimate of what these B frames are before you've transmitted any data. So any residual error that you have in the estimation of these frames is going to be very small, and therefore you're going to have just a small amount of data. I won't say the exact magnitude. It depends on the resolution of images you have, etc. But hopefully there's going to be a small magnitude of error here, which means a small number of bits that need to be transferred in your encoded message. So are there questions about that? That we already talked about at the end of last class, so just as a refresher. Okay. So MPEG-2 has actually kind of 13 different standards in one, depending on which type of resolution image you're going to have, depending on the different aspects of the ratio, of the compression. So you can have a high definition, you can have a high 1440 definition, you can have the main profile, which is kind of a standard resolution, and you can have low resolution, right? So imagine that you have poor network quality and you need to have a very high rate of compression, then you might want to send something low signal. And so for each of these kind of resolutions, you're then going to have different characteristics. So there's simple, there's the usual one, signal to noise ratio scalable, spatially scalable, high definition, multi-view, and then if you want to have the different color resolutions, so if you have a higher resolution for grayscale than for your color channels, then you can also have a profile for that. And each of these boxes that has an X in it means that there's an implementation for that. That's part of the standard. Yeah. So it's the same basic principle that we saw before when we were looking at the general idea of transmitting television video, is that once you have a basic standard, then for certain applications, maybe it's relatively simple to just change some aspect of that standard and then in a kind of simple way adapt it to the different types of applications that you might have. So for security video versus normal television versus high definition television, the different aspect ratios, etc. Okay, and in MPEG-4, you have a much more complex model that's built into the standard, right? So you have all sorts of kind of audio-visual interaction, including that you can have voices, 2D background, sprites, right? So sprites are kind of that segmented out video game character type moving thing, so that you only have to estimate a kind of compact spatial representation of something moving around. You have something where you can encode 3D objects. You can have a scene coordinate system, so we're starting to get almost into like VRML type of specifications, where you can actually have 3D models of objects. You can have a hypothetical viewer, right? So that you have the viewpoint encoded in there as well. So you can imagine trying to do things like change that viewpoint, et cetera, et cetera. And then this goes to audio modules that then can connect to different properties of the display, speakers, everything. So all of that information you can basically encode in this huge set of standards. Right? And so you have kind of the usual view that you have multiple channels that are coming in for all of these different sources of information. Then you have to be able to transmit or store them. You have to be able to take those streams, separate them out, or put them all together to be able to transmit across a network. And then once you have them pieced apart into the different components, then you need to be able to interact with them and interface with displays. Okay, so it's a very kind of complex ecosystem of the different channels that can all do interesting things related to multimedia. And so with all of that functionality comes a lot of complexity in the standards, right? So you don't need to get too lost in it, but you basically need to know that for MPEG-4, with all of these different types of channels, you have like 31 different standards that form this overall big package of standards. So if you actually, for example, go and try to look at the Wikipedia pages for these things, then you see you don't get to a page, you get to a category. And then the category has, there should be 31, but I only see 28 here. So web video coding, time, text, and visual overlays, and video coding for browsers doesn't seem to be in Wikipedia. But then as you start clicking on these individual ones, then you see that most of them are just mapping back to the MP4, the MPEG-4 page, where you can see details of it. And then it gives the different information about the different components. Does it have all 31? Yes, it does have all 31 here at least. Okay, so the 3 that it doesn't have are 2014 and under development. So presumably that category page was made somewhere in after 2012, but before 2014. And then if you click on these, then it will take you to the ISO webpage for that, and you can buy a PDF of it for 200 francs. But yeah, so anyway, it's a complex set of things, but if you dig into each of the individual standards, then you will see that it looks a lot like stuff that we've already seen, right? So you have, if it's an audio standard, it will look a lot like the other audio standards that we've seen in detail. If it's a video standard, it will look a lot like the other video standards that we've seen in detail. Okay, so just to give some of the details, if you're looking at the video coding standard within MP4, then you have, for binary shape, you have motion compensation and arithmetic coding. For transparencies, you have, again, motion compensation and discrete cosine transform. For coding texture, you have shape adaptive discrete cosine transform. For still images, you have wavelets, et cetera, right? So wavelets, you might get a more accurate estimation, but maybe it's a bit slower. For discrete cosine transform, you can get a lot of fixed hardware implementations that are super fast. So that's a way of dealing with that. And then coding of motion, you can have kind of this block coding where you estimate if blocks are shifting. And then you have a global motion compensation per object with sprites, right? So I mentioned sprites before. I forgot if we had talked about them in a previous class or no. I think maybe not. So this is a sprite, right? So the idea is that you have kind of the background, and then you have like your little pixelated action figure person here that is representing the pixels that are likely to move. And they tend to correspond with this object, right? This moving object. And so if, for example, you have a person moving in a scene, for example, the tennis player is moving, at the same time that you might have some slight overall camera motion, then having two different motion models is going to be important for being able to do accurate prediction. Right? You can have one motion model that's estimating the motion of the camera, that kind of that global motion, and then you can have the other motion model that's saying on top of this, this person is moving, and so if this person has been running in this direction, then you can kind of estimate the next frame they're likely to have moved over a little bit this way, and therefore you have a higher prediction accuracy, which means lower residual information to encode. And then, as we mentioned before, as a strategy for this type of prediction, you can do a hierarchical prediction where you kind of predict on different scales, and then at each scale you predict the residual that was not predicted by the previous scale. So that way, if you have fine motion, like the motion of the legs relative to the motion of the overall body of the person, then you only have to encode that relative motion. And in doing so, you hopefully have fewer coefficients that you need to store to encode that difference. Yeah, is that clear? So all of that is built into the standard. There's also standards for synthetic video. So for face animation, so this is not a particularly good rendering here, but there are very good face models, right? So just like you think about implementations of character encoding versus fonts, again, with the parametric facial encoding versus the actual rendering, this would be not a particularly accurate rendering, but if we go and we look, for example, at the Basel face model, then let's see. Then you can see that there's actually very good face models that are available. So you can have really very photorealistic renderings of faces that can be controlled by very few parameters. Right? So you have, some tens of parameters, and that can correspond to a lot of kind of intuitive facial expressions. So there's been really a large amount of work that's been done on this over the last 20 years or so. So it can be, in fact, a very good way of doing things. And I'm sure you've seen movies that have had basically entirely synthetically rendered faces that look almost photorealistic. And so they use models kind of in that direction. Maybe not that exact same model. So yeah, even though this slide from this example, it looks a bit like it's a really kind of esoteric cartoon type of thing that you wouldn't really want to use that much. In practice, having that as a standard is very important because it means that you do have a very efficient encoding of that information included within the standard. And you can get very good photorealistic renderings. Okay, so you have some extensions. So you have advanced video coding, where you use an integer transform instead of a discrete cosine transform. You have intra-frame block prediction. You have variable block size, quarter pixel motion compensation. And then you have better entropy coding as well based on run length or arithmetic code. And so if you put together all of these things, so you have more motion vectors that you can predict, etc., then you can see that if you model the signal-to-noise ratio as a function of the bit rate, then you do have very much improved SNR compared with the other previous standards. So remember, all of this is not necessarily a question of accuracy, right? So you do have a loss in a lot of these encoding schemes, but that loss is effectively the parameter that you can control. And then once you fix a given loss, then the question is how high a rate of compression can you get, right? So if you say, look, I need to have a signal to noise ratio of this 34 here, then you can see, well, I'm going to need about 128 bits, kilobits per second for the improved coding versus more like 256 or even closer to 300 something if you use one of the competitors. Right? So that's the way to think about this curve and read this curve. So higher is better, right? Okay, so if we dig into the standard for sound, then again you have a distinction between natural and synthetic sound. So you're going to do different things depending on where you're at. So if you're in natural sound and you're doing speech coding, well, there's two different ways that you do it. One is kind of more classical encoding type of scheme, where that is adapted to the statistics of human speech. So that would be the first aspect. Or you can have a parametric representation where you're really trying to specifically have common waveforms coming from speech, and then that will be a different thing. And right, so this you're going to have probably a higher quality playback. It's going to be more adaptive to how people are speaking, the different characteristics of speech, etc. But you see, you pay a price and that additional accuracy in terms of the number of bits per second. Whereas if you have this parametric representation, you can get a really high rate of compression. So if you're in some sort of circumstance where you're really constrained for how much bandwidth you can use, then you might want to do that trade-off in terms of sacrificing quality for speed. And then for other types of audio, you're going to have a different encoding scheme, right? Because the statistics of speech are very different from the statistics of music. And so to have a good encoding scheme, we know that you need to accurately estimate the distribution of the signal that you're trying to encode. So, yeah, there's some variance on how it's encoded, but it's quite similar to what we've looked at before. Yeah, so it's using a different coding scheme from Huffman, but it's quite similar to the previous MPEG standards. And then again, there's kind of the more adaptive statistics-based approach, or you can have a more parametric representation where you're, again, going to be trading off the speed and quality. And then for synthetic sound, you can have text-to-speech synthesizers, and then you can also have an orchestra of virtual instruments, kind of in a MIDI music style. Yeah. So are there questions on how sound is encoded? No. Okay, so here is MPEG 7. MPEG 7 is kind of like a XML layer on top of the multimedia coding itself. So it allows for a lot of meta information to be stored about the different types of the different types of media that are actually encoded in, for example, an audio-video stream. So that allows things for doing filters, searches and queries, etc., on top of that video stream, or that audio-video stream. Yeah. So kind of taking a lot of the different components that we've been talking about over the last 3 or 4 weeks and really gluing them together into one really big system, one big standard. So you have a description definition language that says what the types of structures are actually going to be. So this is a lot like a DTD in XML, right? And then you have descriptors, which are the syntax and semantics of feature representation. And then you have descriptor schemes, which specifies the structure and semantics of the relationships between these things. And then you can instantiate this, and that generates the tags where you say it's a scene. The scene is scene number 1. You have information about the time, camera, annotation, etc. And then you have encoding and delivery. This gets converted into a binary stream. It points to a binary stream, and then you can transmit it along with the audiovisual information. So what kinds of applications can you think of for this type of technology? I mean, this is really rich. This is really powerful, right? You had a comment? Do you have a thought about how would you maybe think about using this type of technology?
I'm not sure it's right or not. I will use it to like a VR.
So virtual reality. So in what way? What do you mean by that?
Like AR and VR.
Augmented reality and virtual reality. So I think yes, but that's not specific enough. So how about this? What if we have a recording now of this lecture? What if I could edit this video stream somehow with a bunch of meta information where I could start, for example, putting in web links, right? So you can see me, you can see the screen. You can probably have some sort of controls that can toggle the layout of how you see me and the screen, depending on what's convenient to you. And what if I could make it so that if you put your mouse over the video that corresponds to this DDL box there, I would take you to the Wikipedia page about this. Or if you clicked on MPEG-7, it would take you to the Wikipedia page, or it would take you to a different YouTube tutorial video or something like that. Right? So all this information could be included in that. Imagine that you're doing movie production, right? And you want to store a lot of different metadata about different things that go into different versions of a take, right? So you have a bunch of different takes, and maybe you want to say something about where different objects are in the scenes and what their interrelationships are, and you need to encode that somehow, and you use that, for example, for a continuity detection system, right? That would, so yeah?
Wait, so you need to specify it, or I thought the feature extraction part will automatically detect.
Well, it depends, right? So this is a framework. This is a standard. It doesn't say how an individual component is necessarily working.
So it's not like it extracts all types of figures.
No. It's not doing that necessarily in any sort of way, right? So just like you have different video streams, different codecs, you could imagine having a different detector as part of a standard. So anyway, this is actually a really powerful thing, right? If you think about it, it's a really cool thing. It's maybe not showing up in a lot of applications that you necessarily have access to, although we can maybe check at some point. I haven't looked ahead of time, but maybe we can see if certain types of video editing software is based upon MPEG 7 standards. But it's really anticipating, I think, a lot of the ways that we need to interact with multimedia information, and a lot of, or that need for kind of a metadata layer on top of just the raw video and audio streams. You're not just sending a video and audio thing. You're not just having a couple EXIF tags or something like that, but you're really having very flexible language of structured information that you can place on top of that. And it's done in a flexible way that through this description definition language, you can implement many, many different things. Yeah.
Is it only for like pre-recorded audio or video stream, or can it be any audio video stream like Skype?
So in principle, I would say no. It's not, shouldn't just be for pre-recorded, because if you go back to the whole idea about MPEG, okay, this is MPEG 1, but not worrying about that too much, is it says a digital storage medium, but it could be coming straight from a camera in real time, right? Or with a slight delay. So suppose that I have a live video stream that's coming directly from a camera, and then I could even have it pass through some sort of visual processing, for example, to do object detection, car detection, pedestrian detection, and then later on maybe then give an augmented output. I don't know if it's going to be fast enough for these types of real-time specifications, but you could, depending on your specific implementation of the standard, you can imagine that some sort of augmented reality overlay in a semi-autonomous car could be based on this standard, right? It would have that kind of flexibility, at least in principle, to provide that type of information and do that type of display. Yeah.
Is Google Glass using this?
I do not know what standards they use. So some of my friends were working on that, but I'd never talked to them about the specific standards. And when I see people from Google at conferences, I try not to have these conversations, because then you quickly get into things where they don't want to answer questions anymore. Because it's their proprietary thing, right? So typically, I mean, it depends on which company you're visiting, but it could be that you even have to sign a non-disclosure agreement to enter in a building, right? So I'm going to be visiting Google in July in Zurich, and they said specifically that I'm not allowed to take any photos or videos. They have all these kinds of restrictions. So yeah, and especially if you work there. Okay, so if you're an academic and you're visiting and then you say something you shouldn't have, or you surreptitiously take a picture, you might get sued by them. If you work there and then you say something that you shouldn't have and then it gets out later, you can get fired, and people don't like to do that. Yeah. But at any rate, I don't know exactly what every company is using, but people are using things like this. So whether you care about this specific standard or not probably depends on which company you're working at, or what type of software you want to use, or what type of setup you're trying to create, right? So if you can take off-the-shelf components and piece them together, and this standard forms a glue for the design of those off-the-shelf components, well, you need to make sure that you know what the underlying standard is and that they're all compatible with each other, or it's not going to do what you want it to do. Yeah? Are there more questions about this? I mean, it's cool stuff. It seems kind of like, oh man, it's just standards, but it enables cool things. Yeah.
Is this like a container format on steroids?
Yeah. It's a container format on steroids. So it's very much like if you think back to XML, right? Or if you think back to the XML based document formats, right? So you have the kind of open office standards or Microsoft Word type standards, then these things are typically based on XML. And then they provide information about maybe a graphic that goes in there. They provide information about what font is going to be associated with different blocks of text. It's going to give information about what style is associated with certain pieces of text. Now, imagine taking that basic concept and expanding it to video, right? So just like in a Microsoft Word document, you can kind of click on URLs and things like that. Or you can have links. It doesn't have to display the URL. It can be any text you want, but it typically gets blue and underlined, and you click on it, and you can take you to a web page, whatever. So just like that, you could have all of that type of functionality and more included in an audio-video stream. Yeah. So an audio-video stream that's furthermore augmented with things like 3D representation of objects and all sorts of stuff. It's a very rich framework. So anything cool that you have to do with it, if you just look at this standard, is going to be a lot of work to build on top of it. But the existence of the standard means that all of that cool stuff is going to be able to interface with it, with different other cool stuff, so long as it's all implemented in a complementary way. Okay. So then there's MPEG 21, which is kind of going even further. So they have things like rights management and stuff like that. I'm not personally super excited about rights management. I like to do things open whenever possible, but I do understand why people are motivated to care about that. And you have, resources, metadata relations, etc. So there's this even bigger movement on top of everything else. So MPEG 21 has digital items. So that's the content, the multimedia data, also metadata and the relations between things. It has rights management. So it has a rights expression language and a rights data dictionary. And then for the different devices that you care about, it's going to have the ability to take a specific media file and then format it and stream it to your phone or your tablet or your laptop or flat screen TV, or maybe you even have a home cinema with a projector, and hopefully through kind of one storage of that file, you might be able to at least cover with reasonable resolution a range of these things. So there's this MPEG-A multimedia application formats, just to really kind of dig in and show all of the different ecosystem around MPEG. I mean, it's this huge thing. If you think about it, you have MPEG showing up and just so many different things that you use on a daily basis. It makes sense that there's going to be a whole standards ecosystem around that for all sorts of individual types of applications. And again, each of these are having their own ISO standards. So you have musical slideshows, media streaming, professional archive, open access, portable video, digital broadcasting, video surveillance, stereoscopic video, interactive music, etc. It's kind of no end to... I don't even know exactly what types of features are included in interactive music, but it sounds pretty interesting. So you have kind of no end to all of the different variants of these things. And then underlying it all, of course, you're going to need to have the basic components, right? You're going to need to be able to encode video and audio in an appropriate resolution with appropriate coding rate. And you're going to need to have whatever other types of metadata on top of that that's going to enable this specific application. So again, you have a lot of different things. So for systems technologies, you have MPEG-B For video technologies, you have MPEG-C. For audio technologies, you have MPEG-D. For multimedia middleware, you have MPEG-E. And for media delivery in heterogeneous environments, so that's like the example that I was giving where you can have streaming to your phone versus your tablet versus other screens. You have MPEG-H. You can have MPEG extensible middleware, which is MPEG-M. MPEG rich media user interface, MPEG-U. Information exchange with virtual worlds, MPEG-V. So there you have additional needs, right? So you can have control so that you can interact with the world, sensory information, avatars. You could use this, for example, for video conferencing, etc. So there's this H.265, which is supposed to push video coding even further. And so the idea was to, or the goal was to try to have an extra 2 times compression factor, and to exploit parallel processing, right? So with graphics cards, the kind of the hardware landscape has been expanding a lot. So if processing can be parallelized, then you can consider a trade-off where you throw more parallel computation for better predictive accuracy. And with that better predictive accuracy, you're going to have a lower residual error rate in your frame prediction, and therefore you're going to have a higher rate of compression. Right? So that's the basic idea. So if you're imagining that you have to have a fixed circuit for something, a fixed hardware implementation, or if you're thinking in kind of a von Neumann architecture where you're going to have kind of sequential processing, then having restrictions in the type of processing, so for example, having fixed block sizes, fixed block structure, and things like that, is maybe a good trade-off for past hardware. But now if we think about having flexible parallel hardware, we might be able to be more data adaptive. So you replace a fixed macro block structure by a quad tree. Does everybody know what a quad tree is? So a quad tree is kind of, it's not a binary tree, it's a tree with 4 branches. Right? So very often you use this in video data. So assuming that you don't know something ahead of time about the spatial structure of something, then it's not too unreasonable to say, okay, I have basically a rectangle or a square. I'm just going to divide it into 4. And now I recurse. Right? So for each of the 4 subblocks, you can do a motion estimation. Yeah? And then you ask yourself, am I accurate enough? Okay, if I'm accurate enough, I can stop. But what if I'm not accurate enough, according to some threshold that I set? Well, then what I do is I recurse. I split that up into 4 again. And then for each of those 4 subblocks, now I have a smaller block. I do a motion estimation. Right? So one way to think about that is to think about this tennis example again. So suppose that I have very slow overall camera motion. So if I estimate from a single block, then I do a very good job of estimating that overall camera motion. But then, let's say that I have a person here that in the subsequent frame moves a little bit to the side. Okay? So now I'm going to do the first quad tree. Right? So I do an estimation and I say, no, I have too many errors in these pixels here. My signal to noise ratio isn't high enough. Yeah? And so what I need to do then is subdivide. And now this block, there's no small motion. So at that point, I'm happy. This block, no small motion, I'm happy. I'm happy. Okay? So now here, I don't need to go further down. If I had a fixed resolution, then to get down to the resolution of this person here, I would have to have the same size blocks everywhere, right? And that would be a lot more processing. So I'd spend a lot of processing on the fact that there's fixed blocks, but I wouldn't ever achieve those efficiencies. I wouldn't focus my processing only on the areas where it's needed. And so here, I'm going to do a subdivision. Sorry, don't do that. Then I do another subdivision, and then I do another subdivision, and then maybe by this point I have a good enough estimation, right? So if I have one point of motion here, what's kind of the overhead of this quad tree scheme? Let's say that I could have, if I were kind of like an oracle, and I could say, well, actually, you know what? The motion is exactly here. So I just put a box around it, and I can estimate motion exactly there. Okay, I can never do this. This is just a thought experiment. But if I could, what's the additional amount of processing that I have to do with the quad tree scheme? How much extra processing do I have to do?
You need to create the tree.
Well, yeah, you need to create the tree and recurse on the tree. But what, in terms of big O notation, how many extra blocks are there? Yeah, it's going to be, so what's n? N is the depth of the tree. Yeah, so that's the number of steps. So if I did an exhaustive search of all blocks of that size, it would be 4 to the n, where n is the number of blocks. That sounds about right, yeah. At any rate, it would be exponential in the depth. But if basically at each point I only need to recurse into one square, then the number of blocks that I have to do is going to be logarithmic. It's going to be linear in the depth, which is logarithmic in all of the boxes of that size. Right? So if you can get a logarithmic speed up, take it. That's the best you can ever get in computer science, basically. So yes, I do have kind of a factor of 3 here. Right? I have to do 1, 2, 3 extra computations for something that's purely background. Right? So that's kind of the constants that you get from the quad part of it. But everything else is actually quite fast. And in terms of asymptotics, in terms of big O, it's a very good rate if you only have small amounts of localized motion. Okay, so you replace that by the quad tree. So that means that it's going to be different for prediction or for transform coding, right? So you have to account for that, but that's okay. You can use discrete sign transforms still. And then it's really similar to this H264 that we saw a couple slides ago. So if I get back to here, yeah. So you see here you have 8 different motion directions that you can predict. And here you say, look, I'm just doing this in parallel. So if I want to do more motion predictions, then I just take another parallel unit and I predict additional directions, which means I have a more fine-grained prediction of the motion. Yeah? So here you have all of these different directions, which is more processing, but if you can do it in parallel, then you won't incur any sort of delay, and then you can get a better prediction and a higher rate of coding. So here you have the years versus compression ratio, and you can see going from MPEG-2 H262 to this advanced video coding H264, you go from like 1/25th to 1/50th, and then with the high efficiency video coding HEVC, the H265, then you're getting like 1 to 100 compression ratio, which is pretty impressive. right? You're sending 1% of the bits of a raw stream. Okay. Digital TV, you have these standards that are defined by these different industry boards. So ATSC, DVB, and ISDB are the main boards that are defining these standards. The features are based on MPEG-2 or possibly MPEG-4 for HD video. You can have multiple transmission channels. You can have multiple use of a channel. So you can have these different encoding schemes, etc. And you can have interactive. So if you have this channel being sent, then you can decide how to output it depending on what device you get. And you can have interactive TV things if you have some of these additional kind of interactive layers added on top of that. Okay. And you understand when it says with or without back channel, that's with or without sending information from the TV back to the sender. Right? So if the sender sends multiple streams or multiple information, then you can have interactive TV that basically selects among the information that it's sent. Right? But similarly, you could have interactive TV that also sends, the person, for example, there's a survey, and it says, do you approve of something or disapprove of something? And then you can say, yes, I approve of that, and then it can send that information back. Right? So either the sender can record that information or not. So that's with or without this back channel. Okay, and then if you look at the DVB transmission model, basically the idea is that you have different types of transmissions that are coming into this integrated receiver decoder. So you have some sort of box, and then that box can then connect to all your different devices. And then you can also have some sort of cable that gives you an interactive relationship as well. Okay, so that's kind of the overview of standards. Believe it or not, we got to the end of standards. So I know there's been a lot, but hopefully at the very least, number one, you have a basic idea of what the ecosystem of standards are, how they arise, what kind of the politics and economics of standards are, and then going into it knowing the details of standards for, at the very least, audio and video, knowing how that relates to other types of text and kind of 2D print layout type of content, knowing about meta languages that go on top of things like XML and things like that, where you can define all sorts of metadata about the underlying content, be that text or video or audio or a combination of all of these things. And then knowing about the actual coding that goes into sending a compressed audio or video stream. So what are maybe the main things to know about sending audio? What's the basic outline of a state-of-the-art audio transmission standard? What should be included? It's time for a break, but we can just stand here until... yeah. So what goes into an audio standard? I'll give you a hint. The first thing is that you have to define the type of audio? What are the main types of audio that you might want to split up?
Voice and music.
Yeah, so voice and music are big ones. You also have things like kind of background noise that you might want to have. For voice, you might want to think about the difference between voiced and unvoiced sounds and have, kind of specific components for each of those. So remember the sh versus zh. These two things have different audio characteristics. Then what? Let's say now you're either dealing with voice or music. Let's say you know that you're dealing with music. What is the audio codec going to do?
Wavelet's transformation
Okay, transform the data how?
to frequency domain.
Transform to frequency domain. Exactly what I was looking for. Then what?
Quantization.
Yeah, so you're going to do a quantization. You may or may not do a prediction. And then you do a quantization. And then?
Encoding.
Then encoding. So for everything, it's basically the same. You do transformation also in video, right? You're going to do a transformation into the frequency domain. That could be through discrete cosine transform. It could be through wavelet transform. But you first basically have some kind of transform from spatial to frequency. And then once you have that frequency information, you're going to do some sort of compression of the number of bits. For temporal sequences, you can do a predictive coding, right, where you predict the next thing from the previous ones, for example. And then you take that resulting thing that you need to compress, you round off the bits, you throw away the small bits, and then you do some sort of coding, right? Some sort of entropy-based coding. Could be arithmetic coding, could be Huffman coding, could be run-length coding if you have a lot of zeros, right? And then once you have that, you send it off over the network. And then you have basically an inversion of that process at the receiving end. Okay. Yeah. So that's the basics. Are there questions at this point? Let's say we can take now like a 10-ish minute break. So if you come back at about 12 after, I can stick around during the break and answer questions if there are any. Okay.
It's like if you ask me specific and like tell me.
Yep. Yeah.
So, if it's say n is the amount of blocks, or n is the amount of steps that we go in.
Okay, so it depends on how you want to think about it. Let's say that you have let's say that you take this and you would break it into a fixed trying to come up with indices that don't include n. A fixed q by r set of blocks, right? And then let n be equal to q times r.
Wait, but the different blocks.
Right. So the thing is that the aspect ratio might not be square, right? But let's say that the aspect ratio is exactly square, just for simplicity. Okay, and then q is equal to r. So you have q squared, n is equal to q squared. So let's say that I have 1. So
Okay.
so I have a 5 by 5 grid. So I have 25 different blocks. Yeah? Now, actually I want this to be a power of 2. 1, 2, 3. Okay.
它这个每个 sequence 就是这个，
没有，这个是 sequence 是一系列的图片，一系列的 picture，然后每幅 picture
Okay. So I have 64 blocks.
很多
Okay, so here's my 64 blocks. And so the naive thing is to, for every block, I do a motion estimation.
看起来是怎么着？
Yeah, yeah. Or I do a quad tree, and I break it up, and I do 1, 2, 3 blocks. And actually, good, this is exactly the right resolution here. And then I have to do a quad tree again here, and then I do a quad tree again here. No, actually, I did one more here, and I do a quad tree again there. But let's pretend that I don't. So I do a quad tree again there. So let me get rid of this final subdivision. So now the resolution is the same. Okay. So here I do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, as opposed to 64.
减小你要传的数据量，那么你就可以从你原来的
I was counting the number of blocks. So the point is, though, that for the block estimation, first of all, you can do hierarchical tricks, blah, blah, blah. And then second of all,
减小你要
you can you can do this parallel processing tricks as well, right? So you're checking a fixed number of directions of motion. Here, this is the one that's here. So you have a fixed number of directions. This is the big number, but for the previous one you had 8. Yeah, you had 8 different directions that you're checking. So then for each of these you have to do like 8 different things, but it's, trust me, this is cheaper than this. Yeah. Because you're only at the end assigning one motion direction to each of these blocks. So yeah, you do have like a benefit of this early stopping kind of thing. So this is 10 and this is 64. That's finite. Now imagine that this would go infinite. Then asymptotically it's logarithmic. It's a constant times the logarithm is the expected number here if there's only one thing moving versus here. So it's just be careful of asymptotic analysis. Maybe don't get too involved in my explanation, but just know that this is more efficient and that there's a nice theoretical argument underneath that's saying that it's kind of fundamentally more efficient, and then in a kind of asymptotically optimal way up to a multiplicative factor.
What is that?
Well, it comes from the fact that there's a log base 4 as opposed to a log base 2 or whatever. So, if you change from one logarithmic basis to another, then you have like a constant that goes in front of that, and then you have a constant amount of processing time per square. So how would you do a binary tree for this?
就是减嘛，
Right, but then you end up with different aspect ratios, and you have to have then different ways of handling the vertical versus horizontal splits. So if you do a quad tree, you have the same aspect ratio every time, and as if your motion estimation is somehow based on downsampling to some fixed resolution, and then comparing on some fixed resolution,
然后从负的方式，
then you can use exactly the same code for every single part.
然后差不多，那你就肯定要用，反正我就用了2个计数器，一个算
Horizontal? Yeah, so in principle you could do that. In practice, if you're doing the quad tree, regardless of the motion, the type of motion, you're only going to incur a constant penalty over any sort of specialized scheme, right?
I see, so it's more.
So and again, that has to do with this kind of logarithmic thing. This logarithmic analysis says that eventually, because it very quickly can narrow down to the location of the motion, then at some point you're going to, like, let's say that there's a tall thing that's moving like this, and it's always a tall thing that's moving like that. Then at some point, you're going to have 2 blocks instead of 1. But then you don't have to be biased towards certain types of motion ahead of time.
很难确定你真实的那个风。
And again, you don't have to have specific processing for different aspect ratios. So it's a very generic thing that will deal with a lot of different types of motion. I mean, yes, it is true that the overall statistics of vision, I don't know, maybe you can come up with a better scheme that's based on that. So I think the point is that it's an improvement over the, just fixed block size. But I think that it's not to say that it's 100% optimal.
Because if we usually
Yeah, but there it could be, but at some point when you have really optimized code, certain you can sometimes have optimized code that's really really optimized, and quad trees can be done really really fast, right? So think about the fact that you're just dividing things by 2. Then it's basically, to find the new coordinates can be just shifting the bits over by 1, right? So if at some point you have to say, if it's like this, then do something like this, and if it's like that, then do something like that, then all of that if then else logic can in the end be more than twice. So let's say that I get up to a factor of 2 within the optimal in terms of the number of blocks this way. If my if then else stuff has more than twice as much logic going into it than just shifting by 1 bit, then it might be faster to do it this way. So in my own personal experience, I don't often run into these factors, but there have been a few times in my research where it's kind of like I've done something much more clever and it works worse. Yeah.
然后那个阿尔法计划。
Okay, so is everybody excited about microphones? Yeah. So here we're into the last main section of the course. So we'll finish this by next week. And it's how to have output. So I think that the overall structure is clear, but just to get the big picture of where we are, and maybe it's also good to remember everything that we've covered in the course so far, since we're getting close to the end and we started a couple months ago. So we started with characteristics of sound and vision. So about how sound is generated, how sound is transmitted, what those various properties are, and how sound is perceived by us, and similarly for vision. So we need to know about the properties of propagation of sound in air. We need to know about the properties of how our ear perceives sound, etc. And then similarly, we need to know about light and how our eyes detect light. Then we talked about how data get compressed, because that's very important, as we've seen, for the specific standards about how to transmit media, and how to store media, and how to store metadata associated with media. And then our standards block was actually by far the longest block that we had to deal with. And it wasn't necessarily the most scientifically complex part of the course, but there's just so much complexity that goes into it, basically because of companies and the way that that we need to have interoperability among different organizations building devices and software all around the world. And then now we're going to talk about how do we record things and display things. So how do we get from the real world into a digital signal, and how do we get from a digital signal back into the real world? That's what you're going to test about. Okay, and we're going to talk first about sound. So there's always two steps involved in sound. It's true of our ears as well. First, we have that a sound pressure gets converted into a mechanical motion. And then we have that a mechanical motion gets converted into an electric signal. And so for a microphone, we have that we have some acoustical signal that gets converted into a mechanical signal, for example, by a diaphragm motion. So that's either measuring pressure or measuring the pressure gradient. And then we have a mechanical signal that gets converted into an electrical signal. And then in the loudspeaker, it's kind of the inversion of that process. So actually, I did not yet check the sound, so I'm hoping this is going to work. Let's see if I can... yeah. Click. Okay, I'm hoping that this is going to work. So we're just going to start off with a really simple video. This is a video that's produced at the... oh, what happened there? Yeah. Okay, good. So I'm sincerely hoping that... Okay, I'm hoping that this is going to be audible. So if it's not, let's see. Okay, so just a little bit about this video. It's intended for people at music school. So these could be classical musicians. It's not intended for technical people, so it's very simple, and it should be quite understandable.
I've been producing music for about 5 years now, but I've been more serious about it for the past year and a half. Today I'm going to be talking about the different types of microphones and how they work. First of all, let's just remind us what a microphone is. A microphone is an input transducer. It transforms one kind of energy into another, or in our case, it converts sound pressure variations into voltage variations, also known as an audio signal. We'll be talking about two kinds of microphones in this video. First of all, the dynamic microphone, which is great for on-stage performance. It isolates the sound source, which is great for loud environments, and it's very robust, so we don't have to fear about it breaking. We will also be talking about the condenser microphone. Condenser microphones are great for studios. They're very sensitive and will replicate the sound recorded very accurately. However, you will need to power this using phantom power or 48 volts. Let's start with the dynamic microphone. A dynamic microphone works by electromagnetic induction, which means it uses a magnet to generate the electrical current. In the head of the microphone, there's a diaphragm, usually made out of plastic or rubber, which will receive the sound waves. Attached to the diaphragm is an induction coil or wire, and when the diaphragm vibrates, the coil goes into the magnetic field of the magnet, which creates an electrical current, your audio signal. This also explains why a dynamic microphone does not need an external source of power to function, because it's generating its own power. However, one diaphragm won't be able to accurately reproduce every audio frequency, and some microphones will use multiple diaphragms for different frequencies and then combine all of these frequencies as one single audio signal. This option is quite expensive and rare, and that's why you most commonly see dynamic microphones specialized for certain frequencies, for example, for bass or for vocals. Let's talk about the condenser microphone now. The condenser microphone uses two metal plates to create an electrical current. One of these plates is a diaphragm, which will vibrate to the sound waves hitting it, and the other blade is stationary, meaning it doesn't move at all. An electrical source provides current, which will pass through the plates and create an electrical field between the plates. This electrical source used to be a battery, but today it is much more common for condenser microphones to use phantom power.
So he keeps talking about phantom power. Phantom power just means that you send an electrical power through the actual transmission wires. So you're using the wires for two different things at the same time.
As the diaphragm vibrates, the electrical field changes, which results in your audio signal. This explains why condenser microphones are better for studio uses. If the amplitude of the sound waves hitting the diaphragm is too big, the two metal plates could touch and ruin the microphone. And since in a studio environment, the total amplitude is usually not as high as on a stage, it's much more or less likely for a condenser microphone to reach that threshold, which could damage the microphone. Thanks for listening to my...
So that's the basics of it, right? It's actually not too complicated. You have that the waves, the pressure waves, hit a diaphragm or some sort of surface. That surface vibrates, and then there's going to be some sort of magnetic induction that converts the vibration into an electrical signal. Okay, so that's the whole principle of how a microphone works. But there's going to be different properties of the microphone depending on the design of how those basic components are put together. So the pressure microphone, that's kind of the first microphone that we were looking at or thinking about, is that you have this diaphragm, right, that's vibrating. And so you have that the pressure is more or less constant, and then the variation in the diaphragm is going to be more or less proportional to the pressure. So at low frequencies, this is going to be effectively omnidirectional, because you have, so for example, the direction 1 here coming straight on, the sound waves will hit that and change the pressure. For direction 2, it's the same. For direction 3, it can come around and touch. And if it's a low frequency, then you have a good propagation of the waves, and you're going to have basically a good response in all directions. But for high frequencies, it's going to be more unidirectional. So you can have reflected waves, you have difference of arrival times, and shadow effect, right? So you have the case is going to provide a shadow effect in that that's going to filter out some of the of that signal that's coming in from behind that. So just to understand how off-axis waves can affect that. So if you have a low frequency sound, then the wavelength is very long, right? And if you think about these waves hitting from an angle like this, then the waves, even if they're hitting at some different time as you go from one side of the membrane to another, it's more or less going to be hitting at the same part of the waveform, right? So if it's hitting at the same part of the waveform, then you're more or less going to have the waves all adding in the same way and contributing in the same way. But if you have a higher frequency, then you can imagine that the point along this waveform that you hit the membrane is going to differ depending on how far that wave has traveled. And so then you can start to get cancellation, right? So some of the waveforms, some of it's going to be hitting at a peak, others are going to be hitting when it's at its base, and then you can have these things canceling out. And so as it's reaching the diaphragm at a different phase, then you have the non-uniform diaphragm motion and a reduced average motion or power. Right? And that's going to be dependent on the frequency. Okay, so that's if you're measuring pressure. But what if you're measuring the pressure gradient? So in practice, both sides of the diaphragm are exposed to the sound. Yeah? So you have things that are coming basically through the microphone and things that are coming in the other direction as well. So what you end up with in terms of the sensitivity is like a figure 8 pattern here. So here you have good pickup. Here you have good pickup. You can hear what's being said. But then if you're at 90 degrees or 270 degrees, basically the pressure that hits the front and the back cancels out. Yeah? So you don't hear things in two different directions. In two directions you hear it, and then if you rotate that by 90 degrees, you won't hear it very well. Yeah? Does that make sense? Kind of intuitively, that makes sense? And so, yeah, here's the basic picture. If you have the front and the back, then the sound that's coming around the back has further to travel. And as it has further to travel, it's not canceling out the sound that's coming from the front. And similarly, if it's coming from the back, then coming around to the front has further to travel. But if you're from either side, then the sound that's coming around the sides is basically hitting it with the same force on either side, and that cancels out. Another thing to note is that the frequency response is going to be plus or minus linear up to some constant, and then it becomes 0 for harmonics of that constant. And then in practice, you can add a mechanical or electrical first-order low-pass filter so that you only let through the sounds or the frequencies that fit within this linear response. And then you filter out these higher frequencies so that you don't get some nasty interferences. Okay, so that's the basic designs, right? So you can have the kind of this omnidirectional pressure microphone. You can have a pressure gradient microphone that has this figure 8. But that's not always what you want, right? So actually, before I get into that, I think I can give you this video about a cardioid microphone.
Pattern we're going to listen to is the cardioid. Cardioid means heart. In this case, it means a sort of heart-shaped pattern off the front of the microphone. The keys to this pattern are it listens to the front roughly 180 degrees and it rejects the sound from the back. Let's hear what that sounds like. We have the white noise on axis with the microphone. We're going to move the white noise around. Still have pretty good pickup until we get to roughly 90 degrees where the pattern ends and we're in the rejection mode. Around the back of the microphone, back to 180 degrees. We should have good rejection from this microphone. Back around, about 90 degrees, we'll start to hear it come in, 45 degrees, and right back to on axis. That gives you a pretty good idea of what a cardioid microphone sounds like. Now let's do it with my voice. Reach the microphone. I'll be on axis with the cardioid microphone. I'll move to approximately 45 degrees to still have good pickup characteristics of my voice. I'll start to tailor off around 90 degrees and disappear back here. And as I walk around the back of the microphone, my voice is muted. You should hear me very well. I see me walking around and around. Close to 90 degrees, it'll pick me up again. You have fairly good audio. And the best audio, again, with all microphones is directly front on axis with the microphone. That's the cardioid microphone.
Okay, so I think that it's nice to have kind of the audio example of how that actually sounds. So why would you want that kind of shape? Why would you want a cardioid instead of an omnidirectional or figure of 8 microphone?
One of the main uses is in studio. You want to isolate room sound from instrument sound.
Okay. So you can achieve that with some sort of sound absorbing materials to be put on all the walls. But in a studio, you'd want that. I would say probably a bigger application would be in a concert hall or in a room like this, right? So let's say that I'm talking, and actually the sound that you're hearing now is just my natural voice. This microphone isn't connected to anything. I think it's recording there, but not it's not coming out of the speakers. So you're just hearing my voice. But imagine that this was a really big room, and I'm sitting here, and I'm kind of nervous, and maybe I'm typing, or I'm ruffling papers together, or someone in the front row is coughing. Then what you want is that the microphone is pointing at the thing that you want to record and is not picking up stuff behind the thing that you want to record. So that's an excellent application of it, right? And there's that's the main idea of why you would want to have something that has that shape of response. And you can get different shapes using slightly different physics. So we're not going to go into all the details of about how to achieve all the shapes, but I think that having the example of how a cardioid microphone works or how you can implement that is good to know, just to get the basic idea of how these things work. So basically the way that it works is that you have a funny shape, right? It's all just that you have a funny shape of the back of the microphone. So you have the diaphragm here, and then you have this back plate that allows sound in, but it's spaced such that there's a delay. For the sound to actually go through this kind of network and reach the diaphragm takes longer than for it to go in here. All right? And so it's designed so that the difference in time for it to go through this network and reach the diaphragm will mean that any sound that comes around and hits it at the front, so it'll arrive, it has longer to take to get from the back to the front. So if you set up this network just the right way, such that the time that it takes to come around back to the front or to come from the back through this network and hit the diaphragm is the same, then the two things will cancel out. And since it's measuring the pressure gradient, then the pressure gradient of the two waves hitting each other at exactly the same magnitude is 0. Yeah? Whereas if you're coming from the front, then you hit it directly from the front, and then this comes around, and it takes long enough that you can still hit it from the back, but not at the same time, right? It's going to take long enough that it doesn't cancel out. At 90 degrees, then again you have kind of the same type of thing where you have more or less canceling out from the two different directions. But then if you have this 180 degrees, you have this path being blocked here, so it has to come around, 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 and that takes the same amount of time as here and around. So it's a clever design of this acoustical delay network that prevents the sound from the back from being able to vibrate the thing, because it's exactly canceling out the sound that's coming around to the front. And so, of course, you can have other directivity possible using, for example, two diaphragms, and then controlling the electrical signals, how you combine them. Because if you have the two diaphragms, then you basically can have the difference of sound from all different directions, and then you can control how that gets combined to cancel out the directions you don't want and to keep the directions you do. Yeah? So you have the electrodynamic microphone and the electrostatic microphone. We actually saw those in the first video, right? So on the one hand, you have a moving coil, and on the other hand, you have these two metal plates, right? And so one plate is stationary, the other plate is vibrating, and so you can get a very high quality sound. But if the amplitude is too high and they touch, then it can damage the microphone. and we have ribbon microphones here as well. So ribbon microphones are very, very sensitive, actually. So here's two types of these electrodynamic microphones. So here you have a moving coil. So you have the diaphragm, and here you can see the cross-section of the wires that are around this cylindrical magnet. Yeah? And so as this drum vibrates, then these coils are going to go up and down around this magnet. And as they do so, then you can read out the variation in the electrical signal that's induced by that magnetic induction. So this is the formula for the magnetic induction. Basically, the only thing that you need to know is that, so first of all, it comes from Faraday. So if you care about the underlying mathematics, then you can look at the Wikipedia page for electromagnetic induction, and then you'll start seeing the appropriate equations from the slides. Yeah. So remember, this course is not just about memorizing things, but about knowing how to dig into things and find the information. So here you can see this is exactly the formula that's on there. And then that's equal to N for N coils. And then there's this term here. Now it turns out that this term here, in our case, is going to be very simple. It's going to be this magnetic field times the length of the loop. And then you have the change in motion per unit time, or change in position per unit time. So this gives you the voltage. So the point is that you get something that's going to be linear, and if you need to increase the voltage, then you just control N. You have an appropriate number of loops around to make sure that you get that. Of course, you want it to be very light, right? So if the coils are too heavy, then that can reduce your ability to record, for example, high frequencies, right? Because it's going to dampen the membrane. Okay, so a ribbon is a different design. So here you have this U-shaped magnet here. And then you have what really is a ribbon. This ribbon of metal is what gets vibrated by the sound. But these can give you very, very, very high quality sound recordings, but they're very fragile. It's very easy to break the ribbon. So it's even can be the case that if you so a ribbon microphone is usually like a cylinder. It'll be in a cylindrical casing. So it looks like a wand. And you even have to keep it vertical. Because if you store it horizontally, then gravity can stretch out this metal ribbon and damage its ability to record sound. So you can think of these as being very high precision, but very fragile. If you take them out into wind, then the wind can break the ribbon. But very sensitive, very good quality recording. All right, and then this is what you saw in the first video about the two-plate systems, where you have these two metal plates. You have a fixed plate and you have a moving plate. So it has a lot of the same principle of the ribbon microphone, that you have this metal plate that's vibrating. So that can give you good quality sound. But again, if you have too high of amplitude and the two plates touch, then it can damage the microphone. And furthermore, if you look at this design, you need to have some charge on this, right? And so typically you need to run the electrical current through the wires in order to get these two metal plates to have the appropriate opposite charge. Yep. You can also have one plate covered with a permanently polarized dielectric material that would mean that you don't have to have a power source in the microphone. But that depends on then a more expensive material. Okay. So are there any questions on microphones? I mean, so the principle is kind of simple. Does anyone have microphones in their project? I forget. Yeah.
Yeah, I have. Infrasound measuring system.
Okay.
Yeah, and it involves the detection of infrasound using the special case of microphone.
Okay. And do you feel that you have enough information now to dig in? Okay, good. Are there any specific questions about this? Yeah?
It's using the same for volcano. I have to somehow monitor a volcano and there's a microphone involved.
Yeah. So you know you can do it?
I just have a question. What if there is a resonancy? Is it a thing? Can that happen for the discs? In this case, I don't know, when you hit the resonancy frequency, and can that damage the microphone as well?
So, I mean, there's this effect, right? So
resonance frequency of the metal.
So you're saying that if there's like a mechanical vibration or something,
or any kind of vibration, which will.
I would assume those are like physically designed to not have any resonance frequencies within the desired use case, no?
That sounds sensible, but yeah, I don't know of the specific characters. I will confess I'm really not an expert on microphones. So it's not an area of research for me or something that I'm not so a lot of audiophiles, they'll read these magazines, and you'll find people, probably hobbyists here in Leuven, that are just normal people living in their houses who are really proper experts on how to set up a speaker system and how to set up microphones and do recordings and all of this. There's a real wealth of information just in YouTube videos. So finding the basic mechanical principles and relating that to the underlying physics is actually less common, kind of surprisingly. Well, maybe not surprisingly. But you have a really high degree of technical sophistication that you can find, but usually without the maths. Right? Because you have a lot of people who are specialized in music, or they're specialized in studio recording, who know a lot about the characteristics of microphones and what the shapes are, and how to store things, and the basic principles about why you have to do things in a certain way, but without necessarily tying it to, okay, this is magnetic induction, and this is the equation, this is the power output, blah, blah, blah. So there's kind of a divorce between those two aspects, the actual underlying physics and the kind of practical implementations of it and all of the devices that are available. So yeah, I don't know about the specific designs, or whether that's for the most part products eliminate those types of resonance frequencies through some sort of mechanical housing design or something like that, but that seems like a sensible answer. Yeah. Okay. Tick here.
Hi, I'm Gary Vaughn, the marketing director for Audio Technica, and I'm here at Sonic Electronics talking about ribbon microphones. Now, ribbon mics are primed for their warm, natural sound, and many consider them to be the purest form of transducers. And actually, these
fall within the dynamic microphone category. So essentially what we have in a ribbon microphone is we have two very strong magnets that are placed on either side of a super thin strip of conductive material, and what we use is a pure aluminum. Now this material is very light and responds very quickly to just very little air pressure. But unlike the wound coil, the traditional mic that you have to drive around, the ribbon movement cuts through this magnetic field and doesn't have much mass. The way that ribbon microphones work, they tend to be very preamp dependent. Now, Audio-Technica, in their 4081, which I'm holding here, this is actually a phantom powered ribbon microphone. So the microphone itself has a small built-in preamp in it, which will drive longer cable runs and makes it much less dependent on preamps that you use externally. While there are pluses to ribbon microphones, there are some drawbacks. Because the ribbon material is very thin and has a large surface area, if you actually blow into the mic or use it in a high wind situation, you can actually damage it because it stretches that ribbon material. You also typically don't want to store your ribbon microphone horizontally because the ribbon can actually sag and that can permanently damage it. Another common problem with older ribbon microphones is that you don't want to feed them phantom power. This can damage the microphone, and this occurs when you plug or unplug microphone cable with phantom power applied. Now again, because the Audio-Technica has 17 patents pending and has a lot of new technology,
okay, you can ignore the sales pitch.
that they actually require it to function, as well as a new proprietary ribbon stamp that we use on ribbon material, which makes it much more rigid. We don't have to worry about how you store it. They're much less likely to damage. So the durability of modern ribbon microphones have really given them a rise in use in live environments, which is traditionally a place that you would never use a ribbon microphone. Again, these are prized for their warm, natural character.
Okay, I don't think that he's going to get to the point that I want him to get to, which is that a ribbon microphone, the pickup is going to be figure 8. Okay, you have a ribbon. If you have the sound wave hitting it directly, it will vibrate that sheet of metal. And then that sheet of metal will vibrate through the magnetic field from the two magnets on either side. And that will give you some electromagnetic induction there. But if you are speaking from the side, then you're going to have the pressure on either side being equal, and the ribbon will remain stationary. Sorry, the ribbon is flat. Maybe it's better to do my hand. But then there's going to be the two magnets on either side of it. So it vibrates like this through the magnets. So as it vibrates through the magnets, then that induces a charge, and you can read the charge directly off the ribbon. Yeah? I don't know if I have this. No, wait, sorry. I don't know if I have the right figure here. Let me see. Yeah, I don't like this picture. Let me see if I can get a better one. Yeah, this is maybe okay. So there's the ribbon that's surrounded by the magnet, and then you're actually reading this off of you're reading the difference in charge via these wires here. So don't worry about this transformer. Right, this looks like a AC/DC kind of thing. So just ignore that. Ignore this part here. The point is that this thing is vibrating through the magnetic field, and then you're going to get electrical potentials coming off on these two wires.
The ribbon microphone is more sensitive than the move.
Yeah. So and think about the material. Think about the material and think about the mass.
The slide shows if you should slide up these two microphones, I can find the.
Sorry, which one?
Exactly this one.
This one, yeah. Yep.
For the moving.
So the moving coil, think about the amount of mass that has to move. That's a lot of mass that's moving.
Yes, but the number, it means one Pascal variation means 2 millivolts.
So if you remember if you remember the sales video, they take the output from the ribbon microphone and then they amplify it. So you have a ribbon microphone that's plugged into an amplifier, or that has an amplifier built in. So there you have a small variation, but very accurate, that you can amplify. For the moving coil, you're already losing information during the recording part, because you have a huge amount of mass that you have to vibrate through this electromagnetic field. Right? So you have to have a lot of ends here, potentially, a lot of loops to get enough. Right? So maybe what you can do here is just divide that by 2, but still you have more mass than you would have with a ribbon. So it's robust, right? You have a diaphragm that you can take outside. There can be wind. There can be all sorts of things. There are places where it's more appropriate to use that moving coil microphone than a ribbon microphone. But if you want to have this very small amount of mass vibrating through the magnetic field and still getting a good signal, then the ribbon mic is a very good quality. You get very good quality, but you have to have it under the controlled conditions that you're not going to damage it. Yeah. Are there any other questions? Okay. Okay, so we've got 9 minutes. I think that we have just enough time probably for speakers, and then the rest we'll have to put off until next week. So just a reminder again, be on time at the beginning of next week, because we'll go and have the lab visit, and it should be fun. It'll be just about half an hour, and I think it's worth it. All right. So the basic idea of a speaker is the same as a microphone. It's just a microphone in reverse, right? So instead of taking the pressure waves, converting it into a mechanical signal that then gets converted into an electrical signal, you take basically the same electrical signal, you put that into something that's going to vibrate a membrane, and via induction again. So now you can imagine, for example, if you wanted to take the same basic model, you have the coils that are fixed, and you have the magnet, or no, actually you want to have the magnet that's fixed because it has a higher mass, and then you have the coils that have the signal going through it, and that signal is going to induce a movement of a membrane. And then that membrane is going to cause the air to vibrate and generate the sound. Okay, so this is the same BNLL from before. Before L was dxdt a couple slides ago. But it's the same equation that we had from the microphone. So that's the force, and that's going to be mass times acceleration. So that's going to be enough. That magnetic induction is going to be enough to vibrate the speaker. Okay, so now we have to remember back to, I think, the very first lecture back in February. Do people remember this formula here? It's the ultimate test.
Acoustic pressure.
All right. Haha. Okay, so we have sound pressure, sound power, and sound intensity remember we made a distinction between these three different things. So sound pressure is kind of the most obvious way to think about things. It's about the actual deviation from an average pressure. And then the sound power is the right way to think about speakers, because a speaker has an area, a surface area, and then you have the pressure and the area are going to be proportional, and then you're going to have some constants that depend on what medium it's being transmitted through. Yeah? Vaguely remember this? Yeah, and it's measured in watts, which should also sound familiar because maybe you've been in the marketplace for buying speakers, and they'll usually say this is a blah 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 watt speaker. Yep. So this is the appropriate thing, and basically what you need to remember is that this is the acoustic power. So it's for the speaker. So it's the power acoustic is kind of a mnemonic, the AC. And you have the power squared times the area divided by some constants. So then let's go back to this. So hopefully this now is going to make more sense. Okay, and now the power in this case is going to be something that depends on these same constants here about the transmission and the velocity, v. Okay, and the velocity is going to be some constant, which we're calling psi here, times omega, the wavelength. More or less happy with that? Okay, so then we plug in this equivalence here. We take that v is equal to psi times omega, and we get this relationship. So we have this c rho psi squared. We're just going to think of that as a constant for the purposes of understanding the properties of a speaker. And then we're going to look at this relationship here. We have a constant omega squared times a. So what that means is that if at a fixed power I increase the area, then I decrease omega. And if I increase omega, so higher frequencies, I need to decrease the area. Yeah? So I have this inverse relationship between frequency and the area of the speaker. So what that means is that you're kind of stuck. You can't design a speaker that's going to sound good for like 7 decades, right? For 7 decibels. Right? So your frequencies are going to be limited physically on your speaker. And this was actually also to a certain extent mentioned in the first video that we saw. Remember when he was talking about the microphone, he was saying about the area of the microphone, that you can basically have a microphone that's attuned to a specific range of sounds, and that you can have multiple diaphragms in the same microphone, but that's super expensive. And in practice, what people do is that they will produce a microphone that works for a specific range. And then, if you want to have a high-quality sound recording of an orchestra, for example, then you need to have a lot of different microphones that are specialized to the different ranges of the different instruments. Okay. And so, that's exactly the same system that we have for speakers, and probably this is starting to look familiar to you too. If you have ever bought speakers, tried to buy a reasonable, high-quality set of speakers to play music. is that you have a subwoofer, you have a woofer, mid-range, and a tweeter are the usual vocabulary for the different ranges. And then you have the filters that divide the audio spectrum into 3 or 4 frequency bands so that you can get appropriate speakers to reproduce the sound at the appropriate frequency. Yeah? Okay, so that's all the time that we have. I've actually stopped on time now for once. So next week is the last time we're going to talk about images and video, input-output, and we'll also talk about 3D at the very end. So I can stick around again for 10 minutes or so if you have questions. Yeah.
I want to talk about my report.
Yeah, sure.
My report is about I need to go to Pyongyang and take some photos and
Okay.
for the game for.
Yeah. So probably next week is going to be the week that's most relevant in terms of talking about cameras and the different aspects of cameras. So first of all, I'll just say that you might get more information then. But do you have a specific question or? Yeah. So it could be that I don't remember all of the projects.